9th International Physics Olympiad, year 1976, IPHO. I offer private tutoring for Physics Olympiad preparation. I currently have openings. Message me if interested. My email is fred1996@hotmail.com, or you can use Skype name Eduard F1996. Problem number 1. A hollow sphere of radius r equal 0.5 meters rotates about a vertical axis through its center with an angular velocity of omega equal 5 radians per second. Inside the sphere, a small block is moving together with the sphere at the height of r/2, g equal 10 meters per second square. Question A. What should be at least the coefficient of friction to fulfill this condition? Question B. Find the minimal coefficient of friction also for the case of omega equal 8 radians per second. Question C. Investigate the problem of stability in both cases. First, for a small change of the position of the block. Second, for a small change of the angular velocity of the sphere. Solution for problem 1. Case A. Omega equal 5 radians per second. The block moves along a horizontal circle of radius r sine alpha. The net force acting on the block is pointed to the center of this circle. The vector sum of the normal force exerted by the wall M, the frictional force S, and the weight mg is equal to the resultant m omega square r sine alpha. The connections between the horizontal and vertical components are these two equations. The solution of the system of equations are this one. Force of friction S equal this expression, and the normal force equal this expression. And the block does not slip down if we have mu greater than force of friction over normal force, which is this expression, and after putting numbers we will get 0.2259. In this case there must be at least this friction to prevent slipping. So that was the solution for question A. Question B. Now suppose that omega equal 8 radians per second. If on the other hand we have omega square r cosine alpha over g greater than 1, some friction is necessary to prevent the block to slip upward. So it means that m omega square r sine alpha must be equal to resultant of forces S, N, and mg. Conditions for the minimal coefficient of friction is next one. Mu must be greater than S over N, which is this expression now, and after putting new numbers we have 0.1729. So that was the solution for question B. Question C. Investigate the problem of stability in both cases. First, for a small change of the position of the block, and second, for a small change of the angular velocity of the sphere. In previous questions we found critical coefficients in both cases. In case A, when the body tried to move down, and in case B, when omega is big and the body tried to go up. So it means that in the first case we decrease a little bit mu, the body start to move down. And if in the second case we decrease mu, body start to move up. And let's investigate our questions by quality assumptions. So first, let's investigate first case A, when we have small omega and force of friction going up. So it means that if we little bit decrease our omega, our body start to move down. And if we increase omega, so it means that we just decrease the force of friction and still will not move. Let's check what happened with the angle A. Because our angle is critical, it means that if we little bit move it down, so it means that we don't have enough force to struggle against the force of friction. So it means that the body will stay in this position. But if we will increase alpha, that will be critical coefficient of friction, and our body start to move in opposite direction. So that was first case. Second case, when bodies try to move upward, because omega is big enough and the force of friction going downhill. So it means that if we increase little bit omega, it means that that will be not enough force of friction to hold it, and the body start to move up. If we decrease omega, it means that we don't need to struggle against force of friction, and the body will stay in this position. And the same thing for angle alpha. Suppose that we decrease little bit alpha, so it means that we don't need, in that case, more force of friction to struggle against it, and the body will stay this angle which a little bit less than critical. But if we will increase alpha, we have to increase our critical force of friction, and the body will go back. So we just investigate all these cases. We see that in all cases it means that when the body tries to go one way, it will stay there. If it's going other way, it will go further. So that was the main reasoning for this question number C. That was a solution for question number C, and for whole problem 1. 9th International Physics Olympiad year 1976 IPHO. I offer private tutoring for Physics Olympiad preparation. I currently have openings. Measure me if interested. My email is fred1996@hotmail.com or Skype name Eduard F. 1996. Problem number 2. The walls of a cylinder of base 1 square decimeter. The piston and the inner dividing wall are perfect heat insulators. The valve in the dividing wall opens if the pressure of the right side is greater than on the left side. Initially there is 12 gram helium in the left side and 2 gram helium in the right side. The lengths of both sides are 11.2 decimeters each, and the temperature is 0 degrees Celsius. Outside we have a pressure of 100 kilopascal. The specific heat at constant volume is CV equal 3.15 joule per gram and Kelvin. At constant pressure it is Cp equal 5.25 joule per gram Kelvin. The piston is pushed slowly towards the dividing wall. When the valve opens, we stop, then continue pushing slowly until the wall is reached. Find the work done on the piston by us. Solution for problem number 2. The volume of 4 gram helium at 0 degree Celsius temperature and pressure of 100 kilopascal is 22.4 cubic decimeters molar volume. It follows that initially the pressure on the left hand side is 600 kilopascal, on the right hand side 100 kilopascal. Therefore, the valve is closed, and adiabatic compression happens until the pressure in the right side reaches 600 kilopascal. So we have gas constant K equal Cp over Cv, or 5/3. And due to adiabatic process, we have this formula for how to find what is final volume in the right part, and that will be 3.62 cubic decimeters. From adiabatic gas equation, we can find what is temperature T2 in this moment. That will be PV over NR, or 552 Kelvin. During this phase, the whole work performed increases the internal energy of the gas. So it means that W1 equals CVM multiplied by temperature difference, 552 Kelvin minus 273 Kelvin, which is giving us 1670 joule. Next, the valve opens, the piston is arrested, the temperature after the mixing has been completed. So finally, after whole mixed, we have temperature equal 313 Kelvin, and during this phase there is no change in the energy, no work done on the piston, and adiabatic compression follows from 11.2 plus 3.62, which is 15.05 cubic decimeters, to 11.2 cubic decimeters. So after new adiabatic compression, we finally get that new temperature is 381 Kelvin. So after whole work done, we have W3 equal 3000 joules. Now we have to subtract total work done by atmospheric pressure, which is 11.2 multiplied by 100 kilopascal. That will be 1120 kilopascal. And after all, we can count what is total work. That will be 1760 plus 1300 and minus 1120, which is 3640 joules. That was solution for problem number 2. 9th International Physics Olympiad, year 1976, IPHO. I offer private tutoring for Physics Olympiad preparation. I currently have openings. Message me if interested. My email is fred1996@hotmail.com, or Skype name Eduard F. 1996. Problem number 3. Somewhere in a glass sphere there is an air bubble. Describe methods how to determine the diameter of the bubble without damaging the sphere. Solution for problem number 3. We cannot rely on any value about the density of the glass. It is quite uncertain. The index of refraction can be determined using a light beam which does not touch the bubble. Another method consists of immersing the sphere into a liquid of same refraction index. Its surface becomes invisible. A great number of methods can be found. We can start by determining the axis, the line which joins the centers of sphere and the bubble. The easiest way is to use the tumbler over method. If the sphere is placed on a horizontal plane, this axis takes up a vertical position. The image of the bubble seen from both directions along the axis is a circle. If the sphere is immersed in a liquid of same index of refraction, the spherical bubble is practically inside a parallel plate, figure 1. Its boundaries can be determined either by a micrometer or using parallel light beams. Along the axis we have a lens system consisting of two peak negative lenses. The diameter of the bubble can be determined by several measurements and complicated calculations. If the index of refraction of the glass is known, we can fit a plano-concave lens of same index of refraction to the sphere at the end of the axis, figure 2. As ABCD forms a parallel plate, the diameter of the bubble can be measured using parallel light beams. Focusing a light beam on point A of the surface of the sphere, figure 3, we get a diverging beam from point A inside the sphere. The rays strike the surface at the other side and illuminate the cap. Measuring the spherical cap, we get angle phi, and angle psi can be obtained in a similar way at point B. From there we have sin phi equal small r over big R plus d, and the sin psi equal small r over big R minus d. And from here we can count what is r and what is d. That would be these solutions. The diameter of the bubble can be determined also by the help of X-rays. X-rays are not reflected by glass. They will cast shadows indicating the structure of the body, in other case the position and diameter of the bubble. We can also determine the moment of inertia with respect to the axis and thus the diameter of the bubble. So that was solution for problem number 3.